Hello, fair weather friends. 'Tis the season, Christmas coming upon us. Let's not be naughty, let's be good boys and girls and solve some algorithmical problems. Proceeding with this, going to our favorite website, Leetcode.com, and opening problem 1696, jump game 6. Many sixes here. You're given a zero-indexed integer array nums and an integer k. You're standing initially at index 0. In one move, you can jump at most k steps forward without going outside of the boundaries of the array. So from I to I plus 1 up to I plus k. Your jump can be at least 1 and at most k steps forward. You want to reach the last index of the array n minus 1. Your score is the sum of all nums j for each index j you visited in the array. Return the maximum score you can get. What you do is, you start from the first element, you need to reach the last element, and every element which you step on your way, you kind of pick up with you and add to this total sum. So what's the maximum score? This problem screams really hard. This problem screams dynamic programming. There is an obvious recursive relationship. The current element score, I, is equal to the best score of the k previous elements plus the current element. Right? This solution would be quadratic. Here is how it would go. You have, maybe let's name this score. Your score at element 0 is element 0. And then you loop through the rest of the elements. You start with integer min value, which is the minimum possible value. And we don't start from 0, let's say, because if you notice in the constraints, our elements can be negative, from minus 10 to the 4th. For every element I, we go through the previous k elements. J's are variable that goes through them. And then we look at the score j plus our current element nums I. If that is more than the best score we've found so far, then we preserve that result. And in the end, we return the score of the last element n minus 1. Very simple dynamic programming solution, quadratic in time, which is a bummer because the number of elements in our array is way too high for a quadratic solution to work. This problem is really interesting because you can optimize a lot after you come up with the original dynamic programming idea. By the way, I wouldn't qualify it as medium. That's definitely a hard problem. It would be medium if the simple dynamic programming solution was working, and it's not. One observation that's really important is you would step on every positive integer in this array. You would choose to step on them. There is no reason to jump over positive numbers, or zeros for that matter. They would always improve your score. Once you know every positive number is valuable and you should go through it, you can actually improve on this solution and prune it, break early when you reach a previous positive number, because for sure you will come from there to your current number. You wouldn't need to go further back. You would have never skipped that positive number. So if nums j is more than 0, you can break. You've already taken that j score, and for sure going further back won't give you a better result. This is okay, but based on the test cases, it's still quadratic in the worst case if you have only negative numbers. You can improve further if you realize that from all the k previous numbers from which you need to jump to your current number, you need the maximum score. And how do you keep the maximum score amongst k numbers and you always surface that maximum? Well, the obvious candidate is a heap. You can use heap, in which you keep the previous k elements, and every time you go through a new element, you add their score to the heap, keeping the maximum on top. Whenever you need to calculate the score for the current element, instead of going through all the k elements in linear time, you can in constant time take the top element. Preserving the invariant of this heap, preserving its correct state, would require log k time when you're bubbling up and down elements. Heap is good. Your total runtime becomes now on by log k. However, you can improve this even further. You can use a monotonously decreasing queue, mono queue, to preserve only the elements you're really interested in. The asymptotic runtime of this solution would be O of n. Here's how a solution like that looks, and I'll explain why do we use a queue. When we are at the current element, we need to jump back up to k elements. Now, if there is a very big element somewhere in those k elements, there is no point to go to the smaller elements before it. We will never have to go further back than our biggest element. Eventually that element will be dropped out, it will get out of reach because we'll continue progressing forward, and so we only can keep the last k. As it goes out, we need the next biggest element, and so the next biggest and so on. And every time we reach a very big element, we can get rid of all the smaller elements before that one, because we would never have to go further back than our biggest element. The idea is preserve the biggest element here, and then the next largest, and so on, until you reach your current element. If there is somewhere a dip, some smaller element, and then a larger than that smaller element, we don't need the dip, right? The element with the small score. We would never have to go back to it because we have a better one closer to our current index. Therefore, the monotonously decreasing nature of this queue. Here's what the code looks like. We'll keep the indices and we'll keep the scores. We need to keep the indices to be able to calculate when we have proceeded so far that we can drop an element from our queue. It's unreachable because our jump is at most k. The indices are needed. We also need the scores so that our queue is ordered by scores in a monotonously decreasing manner. We create a queue with the indices and we push index 0. We also record the score of index 0, which is num0. Then, on our current move, we would look at the first, or in other words, oldest element in the queue, and check if its index is smaller than I minus k. That means it's too far back and we can get rid of it. We'll remove it if that's the case. Next, we will calculate the score of our current index, which is always with no exceptions, the biggest element of our monotonously decreasing queue plus our current element. And the biggest element of that queue obviously is the first element of that queue. Then we go through the queue from our current element back to the first element, and until the queue has elements on it and until the next element is smaller than our current score, we'll get rid of them. We'll remove everything so that when we append our current score, it's still a monotonously decreasing queue. Keep removing the last element until we can insert our current score. We'll do that at the end, insert it, and proceed with the next iteration of our loop. Once we iterate over all the elements, we'll at the end return the score of our last element, right here. This problem has been asked by AQR Capital Management LLC. It's definitely a tricky and thought-provoking question, worth exploring in depth. Quite an interesting solution. There are some other ways to solve this problem, like segment trees and others. Take a look at the discussion section, think about it. Maybe you'll come up with something even more original and mind-blowing. Alright, that was Jump Game Christmas Edition. I hope you had fun. Think about it. Think also about your jump game in life. What's your next goal? Where do you want to jump to? Let me know. And keep coding. See ya!